Kylo Limit Loren back talking to you about properties of continuity. What do you call Chewbacca when he gets chocolate stuck in his fur? A chocolate chip Wookiee!
Okay, so we're going to review this again. The first vocabulary term is continuity at a point. That says a function f is continuous at c when these three conditions are met. The first would be f of c is defined. That means at x is equal to c, your function has a point. There can't be a hole or an asymptote at x is equal to c, otherwise it won't be continuous. The second condition would be that the limit as x approaches c of f of x exists. So we talked about this for a while. We need to know that as x approaches c from the left and the right, your function is approaching the same y value. So here you can see the limit as x approaches c of f of x exists because as x approaches c from the left and the right, your function is approaching the same y value. Over here, as x approaches c from the left and the right, they're approaching two different y values. There's a jump discontinuity there. Therefore, the limit as x approaches c of f of x does not exist, and this function would not be continuous. The last condition that needs to be met is that the limit as x approaches c of f of x equals f of c. So we see here that the limit as x approaches c of f of x from the left and the right exists, and it is equal to f of c. The y value that your function approaches as x approaches c from the left and the right is the same as the y value of the point at x is equal to c. Here, the limit as x approaches c from the left and the right exists, and it's equal to 1, but the point for the function at x is equal to c is at the y value of 3. We have a point at c, 3, but our limit as x approaches c from the left and the right is equal to 1. Therefore, this function would not be continuous at x is equal to c. The next review vocabulary term we're going to talk about is continuity on an open interval. And this says a function is continuous on an open interval ab when the function is continuous at each point on the interval. Just to review, we know an open interval means that we have holes at each of the endpoints rather than points that are filled in. Next, we know that this just makes sense. Continuity on an open interval just means that a function is continuous at each point on the interval. So each of these three conditions must be met at every point along the open interval AB. Here, we see that f of c is defined, so that checks out. The limit as x approaches c of our function f of x, however, does not exist because as we approach c from the left and from the right, we're approaching two different y values. So that condition would not be met and this function would not be continuous. However, here for g of x, g of c is defined at every point. The limit as x approaches c of g of x exists for every point on the interval, and the limit as x approaches c of g of x is equal to g of c for every point on this interval as well. Now, continuity on a closed interval says a function f is continuous on a closed interval ab when f is continuous at each point on the open interval ab, and the limit as x approaches a from the right of f of x is equal to f of a, and the limit as x approaches b from the left of f of x is equal to f of b. All of the same rules for an open interval apply to continuity on a closed interval. A function is going to be continuous on a closed interval if those three conditions are met for every point on the open interval AB, and if the endpoints are filled in, if there are no removable discontinuities on the endpoints. Okay, that's what these are saying. It means that the limit as x approaches a from the right of our function has to equal f of a. That point must be filled in. Same thing over here. The limit as x approaches b from the left of our function f of x has to equal f of b. That point must be filled in right there. Now, properties of continuity. This says if b is a real number and f and g are continuous at x is equal to c, then the functions listed below are also continuous at c. So first, the scalar multiple, b times the function f. So if we multiply our function by a number, it is also going to be continuous at c. If we have a continuous function multiplied by a number, then this new function, after we multiply it by a number, is also going to be continuous at c. Some are different. If we have two functions that are both continuous at some x value c, and we add them together or subtract them, then that new function is still going to be continuous at c. The product property says if we have two functions that are both continuous at x is equal to c, if we were to multiply those two functions together, then that new function would still be continuous at x is equal to c. And lastly, if we had two functions that were both continuous at some x value c, and we divided them, then that new function would be continuous at x is equal to c. Next, we're going to talk about continuity of a composite function. So this says if g is continuous at c and f is continuous at g of c, then the composite function given by f of g of x, which is also written f of g of x, is continuous at x is equal to c. So this is a little bit confusing. What we're going to do is use this example down here to help you understand it. So this says discuss the continuity of the composite function h of x, which is equal to f of g of x. So h of x is our composite function f of g of x, and we have f of x equal to 1 over x minus 6 and g of x equal to x squared plus 5. So to determine if our composite function is continuous at some x value, let's call our c 2. So let's determine if this composite function is continuous at x is equal to 2. First, we need to figure out if g is continuous at x is equal to 2. Is there any hole or asymptote for our function g? No. This is a parabola, therefore there's no hole or asymptote for this particular function. So g is continuous at x is equal to 2. Next, we need to figure out if f is continuous at g of c. So what is g of 2 in this case? G of 2 would be plugging in 2 for x, and we would get 2 squared, which is 4, plus 5, which is 9. So g of 2 is equal to 9. Is our function f continuous at x is equal to 9? So this function has an asymptote at x is equal to 6. But it is continuous at x is equal to 9, so we're good. So g is continuous at x is equal to 2, f is continuous at g of 2, which is 9. Therefore, our composite function, when we take our g of x function and plug it in for x in our f function and simplify it, this composite function right here would be continuous at x is equal to 2 because g of x is continuous at x is equal to 2 and f of x is continuous at g of 2. Now, if we want to discuss the continuity of this composite function, what we need to do is figure out, are there any holes or asymptotes for this particular function? Well, if we factor this out, we get 1 over x squared minus 1 is the same as 1 over x minus 1 times x plus 1. So we know that our function h is going to have an asymptote at x is equal to 1 and x is equal to negative 1. So if we want to discuss the continuity of a particular composite function, you're going to write your answer like this. The composite function h of x is continuous on the intervals negative infinity to negative 1, negative 1 to 1, and 1 to infinity, with non-removable discontinuities, those would be the asymptotes, at x is equal to negative 1 and 1.
Don't just sit there like a nerf herder. It's example time.
Okay, so example 1 says find the x values, if any, at which f is not continuous. Classify those discontinuities as removable or non-removable, then describe the intervals on which each function is continuous. So here our first function, f of x, which is equal to 4 over x minus 6. To determine this, the first thing we're going to ask ourselves, are there any x values that make f of x undefined? So are there any x values that would cause our function to have a vertical asymptote or a hole? Yes, actually there is. If I were to plug in 6 for x, I would get a vertical asymptote. So which x values would make our function undefined? That would be x is equal to 6. That would create 0 in the denominator, creating a vertical asymptote. Is this a removable or non-removable discontinuity? Well, since it's a vertical asymptote, that would be a non-removable discontinuity. Lastly, we're going to make intervals based on our discontinuity. So our function here is going to be continuous all the way throughout except at the x value 6. So the way we write this would be our function is going to be continuous on the interval from negative infinity to 6 and then on the interval from 6 to infinity. We confirm this with our graphic calculator and you can see that our function is continuous at every point except at the value x is equal to 6. Next, let's talk about tangent of x. We ask ourselves, are there any values of x that would make f of x undefined? Yes, there's actually an infinite amount. F of x, our function, tan x, has an infinite amount of vertical asymptotes. So when we're talking about which x values, it's going to be pi over 2, 3 pi over 2, 5 pi over 2, and so on in both directions. Because of that, we need to create some type of rule that would give us all the x values at which tan x has vertical asymptotes. So it's going to look something like this. X is equal to pi over 2 plus n pi. So we start with pi over 2, and then we add pi times some integer, which will give us both directions, right? Because integers are both positive and negative. And that will give us every x value for which tan has a vertical asymptote. Now, are these going to be removable or non-removable discontinuities? Because they're vertical asymptotes, they are non-removable. And we can make intervals based on our discontinuities. Because there is an infinite amount of discontinuities, we are going to have to put dot dot dots at each end of our intervals. Those are also called ellipses for those of you English majors. When we create our answer, we have the interval from negative 3 pi over 2 to negative pi over 2. Then we have a vertical asymptote at negative pi over 2. We then go from negative pi over 2 to pi over 2 and have a vertical asymptote at pi over 2. We then have our function continuous on the interval from pi over 2 to 3 pi over 2. Then we have another vertical asymptote. Now here we have our graphing calculator. When we plug in tan x, we can see that we have vertical asymptotes at every pi over 2 plus n pi.
I'm sick of trying. You try! I'm choking you. Do you feel it?
Okay, so we're doing the same thing. First, we need to figure out, are there any x values that make f of x undefined? So we look here. Well, it's hard to tell what x value would cause a vertical asymptote down here to cause the denominator equal 0. So what we do is we factor this and see if anything cancels out. So this factors into x minus 2 times x plus 1. And you see that the x minus 2's cancel out. We are left with 1 over x plus 1. So are there any x values that would make f of x undefined, meaning that there would be a vertical asymptote or a hole? Yes, there's going to be a vertical asymptote at x is equal to negative 1. That would cause this denominator to equal 0. We also, remember, canceled out x minus 2. When you cancel something like that out, that's going to create a hole at x is equal to 2, whatever would cause that to equal 0. So we know that there are going to be discontinuities at x is equal to 2 and x is equal to negative 1. So are they removable or non-removable? Well, at x is equal to 2, we have a hole. Therefore, that's going to be a removable discontinuity. But at x is equal to negative 1, there's going to be an asymptote, meaning that's a non-removable. So we actually have both in this case. We're going to make the intervals now based on our discontinuities. So because our function is not continuous at 2 and negative 1, our intervals are going to look something like this. We go from negative infinity to negative 1, and then at x is equal to negative 1, we have a vertical asymptote. Then our function is again continuous from negative 1 to 2. At 2, x is equal to 2, we then have a hole, a removable discontinuity. And then from 2 to infinity, we are then continuous. Okay? And you can confirm this with your graphing calculator, and you see that at x is equal to negative 1, we have vertical asymptote. You cannot really see what the point looks like at x is equal to 2, but I assure you there is a hole at x is equal to 2. For part B, we're dealing with f of x is equal to sine x. So again, we ask ourselves, are there any x values that make f of x undefined? So does sine x have any asymptotes or holes? No, it does not. Therefore, we know that this function is continuous throughout. When we're making our intervals based on our discontinuities, which there are none, we say that sine x is continuous from negative infinity to infinity. And you confirm this with your graphic calculator. You see there are no vertical asymptotes, there are no holes, so it's continuous throughout. Okay, example 2, we're doing the same thing, except this time we have a piecewise function. So we start the same way. Are there any x values that would make f of x undefined? Are there any x values that would cause either part of this piecewise function to have a hole or a vertical asymptote? And the answer is no. This is a straight line, this is a parabola. Therefore, there is no x value that would cause either part of this to have a vertical asymptote or a hole. Next, because this is a piecewise function, you have to do one thing different. It shifts from one graph to another graph at a certain x value. And we have to determine whether there is a jump discontinuity at that x value or not. To do that, we have to figure out whether or not this function is continuous at x is equal to negative 2. So to do that, we have those three conditions we got to meet. So we're going to talk about that. Does the limit as x approaches negative 2 from the left of f of x equal the limit as x approaches negative 2 from the right of f of x? And does that equal f of negative 2? If these three things are equal to one another, then we know that the function, the piecewise function, is continuous at x is equal to negative 2. So let's first figure out what is the limit as x approaches negative 2 from the left of f of x. So as x approaches negative 2 from the left, we're taking x values that are less than negative 2, which means we're using this part of the piecewise function. So to evaluate that, we take negative 2 and we plug it into that part of the piecewise function, and we end up getting negative 5. Now the limit as x approaches negative 2 from the right means we're coming from x values greater than negative 2. So we're going to use this part of the piecewise function. So we take negative 2, plug it in for x here. And when you take negative 2 squared, you get 4 times negative 1 becomes negative 4 plus 2 gives you negative 2. Now you can already see that these two limits do not exist, but if you want to continue on, f of -2 is just taking the function and plugging in -2 where x is equal to -2. So again, that is this part of the piecewise function because this has the little line underneath. And we see that f of -2 is equal to -2 because this was as well. Now, because the limit as x approaches -2 from the left does not equal the limit as x approaches -2 from the right, we're going to have a jump discontinuity at x is equal to -2. So what do we say? Is that removable or non-removable? A jump discontinuity is non-removable, and we can then write our intervals based on that non-removable discontinuity. We say that the function is continuous from -infinity to -2, and then at x is equal to -2, we're going to have a jump discontinuity, and then the function is then continuous from -2 to infinity. We confirm this with our graphing calculator, and you can see that at x is equal to -2, we have a jump discontinuity. Now part B, we're doing the same thing. We have a piecewise function and we first ask ourselves, are there any x values that make f of x undefined? Now immediately you would look at this and say, yeah, at x is equal to 0, this would obviously be undefined. But take a closer look. This function, this piecewise function, has x times sine of 1 over x for every x not equal to 0. But when x does equal 0, the function has a point at 0, 0. So it fills in that spot where there would be a hole. Therefore, there are no x values that would cause this to be undefined. Now, we're not sure if that point, though, would make this whole function continuous, right? Does that fill in the hole, or is it a removable discontinuity? Is there a point somewhere outside of the hole? To answer that question, we have to figure out, does the limit as x approaches 0 from the left of our function equal the limit as x approaches 0 from the right of our function, and does that equal f of 0? Well, we already know that f of 0 is equal to 0. So we need to figure out, does the limit as x approaches 0 from the left and the limit as x approaches 0 from the right of our function equal 0? To do that, we actually discussed this in a previous lesson. We need the squeeze theorem. And the squeeze theorem just says if we have a function that is between two functions, we need to figure out, does the limit as x approaches 0 for the lower function and the upper function equal each other? Because if they do, then our middle function, the limit as x approaches 0 for that middle function, then would be equal to each of those limits. So we take the limit as x approaches 0 for our lower function and the limit as x approaches 0 for our upper function. We get for both of those 0, meaning that the limit as x approaches 0 for our middle function right here is also equal to 0 by the squeeze theorem. We then can say that yes, since the limit as x approaches 0 from the left and the limit as x approaches 0 from the right equals f of 0, then that our function is continuous at x is equal to 0. So it would then be continuous throughout, and we could say that our function is continuous from -infinity to infinity. And we look at our graph right here, and you could see that it would normally be undefined right at x is equal to 0. There would be a hole there. But since f of 0 is equal to 0, our hole is plugged in with a point, and it is continuous throughout.
Yoda's a little green idiot. You try.
Okay, so we're doing the same thing. It says find the x values, if any, at which f is not continuous, then classify the discontinuities as removable or non-removable, and then describe the intervals on which each function is continuous. So here, we have our piecewise function, f of x is equal to sine of 1 over x for all x not equal to 0, and then when x does equal 0, we have f of x equal to 0. So the first question, are there any x values that make f of x undefined? Well, right off the bat, you would think, okay, at x is equal to 0, this would be undefined, but our domain accounts for that. It says f of x is equal to sine of 1 over x for all x not equal to 0. And when x does equal 0, we plug in that point, 0, 0. So there are no values of x for which it's undefined yet. Next, to determine continuity, we must figure out, does the limit as x approaches 0 from the left of our function equal the limit as x approaches 0 from the right of our function, and does that equal f of 0? So the limit from the left of this particular function, the limit as x approaches 0 from the left, well, you look at this function, f of x is equal to sine of 1 over x, and you ask yourself, what does the graph of that look like? Well, remember, it oscillates back and forth between 1 and -1 as x approaches 0 from the left and the right. Because it's oscillating back and forth between 1 and -1, the limit would not exist from the left and from the right, because it does that from the left and from the right. But at f of 0, we are plugging in this point 0, 0. Therefore, f of 0 is actually equal to 0. So these three things are not equal to one another. Now, because of that, we can say the function is not continuous at x is equal to 0. We then ask ourselves, is that a removable or non-removable discontinuity? Because there's a point here, 0, 0, and you're trying to plug that in, and it doesn't plug it in, right? It doesn't make it continuous when you plug in that point. Because of that, that would make it a non-removable discontinuity. A removable discontinuity is like a hole that if you were to plug in a point there, it would make it continuous. Clearly, this is not, because if it were, this right here would make it continuous. So what are the intervals that this function is continuous on? It would be continuous from -infinity to 0, and then from 0 to infinity. You can then confirm this with your graph, and you can see that the limit as x approaches 0 from the left and the right, the graph oscillates back and forth, so it would not exist. And this point right here, 0, 0, even if you plug that in, it doesn't make it continuous. So it's a non-removable discontinuity. For part B, it's the same. Are there any x values that make f of x undefined? You see an x in the denominator and you think, okay, x cannot equal 0. But you can see our domain already accounts for that in this piecewise function. This is the case, f of x is equal to x squared plus x over x for all x not equal to 0. But when x does equal 0, we're actually going to plug in a point, 0, 1. So that means that f of x is defined for all x values. Perfect. Next, does the limit as x approaches 0 from the left of f of x equal the limit as x approaches 0 from the right of f of x, and does that equal f of 0? This determines part of our continuity. We need this in order for a function to be continuous. So the limit as x approaches 0 from the left of our function, well, this is the case for all x not equal to 0, right? So this is from the left and the right. Well, what do? Well, we can't plug in 0, so let's see, can we factor this? If we factor out an x in the numerator, that actually cancels out with the x in the denominator, and we're left with x plus 1. So now we can determine the limit as x approaches 0 from the left. We plug in 0 for x, and we get 1. Same thing from the right. We're using this as well. We plug in 0, and we get 1. So the limit from the left and the right as x approaches 0 is equal to 1. Now what does f of 0 equal? At x is equal to 0, our y value is 1. So f of 0 is also equal to 1. Because all of these are equal and there are no x values at which f of x is undefined, we can say that our function, our piecewise function, is continuous on the real number line. Also see that in our graph, our function f of x is equal to x plus 1 is this red line right here, and the hole occurs at 0, 1, but this part of the piecewise function plugs that hole, meaning that the entire thing is continuous now. Now example 3 says find the constant a or the constants a and b such that the function is continuous on the real number line. So here we just have a. So all we have to do is find a so that this function, this piecewise function, is continuous on the real number line. That means that it has to have the same limit as x approaches 0 from the left as it does from the right. So we set up those limits. The limit as x approaches 0 from the left of our function and the limit as x approaches 0 from the right of our function. And those two things must be equal to one another. So let's start by finding the limit as x approaches 0 from the left. We take this part of the function because that's where x is less than 0, and we find the limit of this. Well, if we were to plug in 0 for this part, we would evaluate this and end up getting 0 over 0. But this is an indeterminate form, so we have to go back and try to simplify this a little bit further. We could say that 4 sine x over x is the same as 4 times sine of x over x. And if we were to break this up, it actually breaks up into the limit as x approaches 0 from the left of 4 times the limit as x approaches 0 from the left of sine of x over x. Now the limit as x approaches 0 from the left of 4 is just 4, and the limit as x approaches 0 from the left of sine of x over x we learned is 1, so that would just be 4 times 1, which is 4. Now we look down here, we have the limit as x approaches 0 from the right is this part of the piecewise function. Now, to figure this out, again, we plug in 0 for x, and we simplify it, and we end up getting a. So the limit as x approaches 0 from the right of our function is equal to a. Now, in order for this function, this piecewise function, to be continuous on the whole real number line, we need these two limits to be equal to one another. So a must be equal to 4 in this case.
Luke is fat and ugly. You try.
Okay, here we're doing the same thing, except this time we have an a and a b, and we have 3 parts of our piecewise function. So we're going to break it up into 2 parts. First, we're going to find the limit as x approaches 1 from the left and the limit as x approaches 1 from the right. Then we're going to find the limit as x approaches 4 from the left and 4 from the right. So let's start with 1. The limit as x approaches 1 from the left of f of x. That would be this part of the piecewise function, so that would be equal to 3. Next, we have the limit as x approaches 1 from the right of f of x. That would be this part of the piecewise function. And to evaluate this, we plug in 1 for x, we simplify, and we end up getting a plus b. Now, these two things must be equal in order to be continuous on the real number line. So we set them equal to one another and we say a plus b has to equal 3. Now, this is not solvable because we have two variables. So what we do is we go on to the next part and we find the limit as x approaches 4 from the left and the right. So the limit as x approaches 4 from the right, that would be this part of the piecewise function, is just equal to -3. The limit as x approaches 4 from the left, we go back to this part, and this time we're going to plug in 4 for x. We simplify that, we get 4a plus b is equal to -3, because these two things must be equal in order for this function to be continuous at x is equal to 4. We then have two equations with two variables that we can solve for using a system of equations. We do that by subtracting these two equations. The b's cancel out. We end up getting -3a is equal to 6. Divide both sides by -3, you get a is equal to -2. We then finish solving this by taking that -2, plugging it back in for a, and solving for b. And we end up getting that b is equal to 5. So when a is equal to -2 and b is equal to 5, this piecewise function is continuous on the real number line.